All right, now we're going to solve the next AP Physics problem. This is a problem of a hollow aluminum cylinder. It says it's 20 centimeters deep. It has an internal capacity of 2.000 liters or 2,000 milliliters at 20 degrees Celsius. It is completely filled with turpentine and then it is warmed to 80 degrees Celsius. The question is how much turpentine overflows, and if it is cooled then back down to 20 degrees Celsius, how far below the cylinder's rim is a turpentine surface? So you might see that the idea here is we're considering thermal expansion coefficient of aluminum. The can, of course, when it heats up is going to expand, so it's going to have a larger volume. But the turpentine inside of it is also going to expand. So the question is the relative rate of expansions. If the turpentine expands more rapidly than the aluminum, then of course it's going to overflow. And then when you cool it back down, then there's going to be less turpentine in. How much less? Well, however much overflowed. And so the level is going to drop below the rim of the can. So that's what we're going to try to work out here. Okay, so let's proceed in the following way. I'm going to draw the can to give you a sense of what's going on. I've already done some of the calculations on scrap paper here, so I don't have to punch into a calculator while I'm talking to you. But the idea is that the can has an initial height, I'll call that height original, of 20 centimeters. And it has a volume, an initial volume. The initial volume was 2,000 milliliters. Okay? Remember that the volume of this is going to be given by the height times the cross-sectional area of the can. So the original area of the can, like this. And the cross-sectional area of the can is going to be just the area of this circle, so the original radius squared. So if we know this 2,000 milliliters is the original volume, and we know the original height is 20 milliliters, that means the original cross-sectional area, this right here, has to be equal to 100 square centimeters, right? Because one milliliter is 1 cubic centimeter, so this is 2,000 cubic centimeters. It's 20 centimeters high, so there has to be 100 square centimeter cross-sectional area. We can use this to find out what the original radius is. Okay, so let's make a table here. Let's talk about the original radius and the new radius. Okay, so I'm going to move this up here. So first of all, the volume, the original volume, V naught was equal to 2,000 cubic centimeters, right, cc. And we don't know what the new volume is going to be. Okay, but we're going to have to figure that out. We know that the original height, h naught, was 20 centimeters, and we want to find what the new height is. And we also know that the original area is 100 square centimeters. We can invert this to find that the original radius is about, I have to round because there's a pi in there, but 5.642 centimeters. You take that and square it, multiply by pi, you end up getting 100 square centimeters. Okay, so then the question is, what's the final radius? Okay, so how do we figure out what the new height and the new radius is? Well, what we can use is the coefficient of linear expansion of aluminum. So we know that the change in whatever length dimension we're interested in for aluminum is the original length dimension times the linear expansion coefficient times delta t. And we know that this delta t right here, we were told that the delta t was what? I think it was, went from 20 degrees Celsius to 80 degrees Celsius. So this was 60 degrees Celsius was a change in temperature. We can look up the linear expansion coefficient of aluminum, which I've done, and the linear expansion coefficient of aluminum, I guess I looked it up, but I didn't write it down, but I calculated these, so we can find how much the height expands by. I guess I didn't write this down, but I put it into my calculator, and you'll just have to trust that I got that value. Oh, yes, I see I do have it. So alpha of aluminum was equal to about 22 times 10 to the minus 6, and that would be in inverse degrees Celsius, or per degree Celsius. Okay, so we can find that the new height of this is going to be 20.0264 centimeters. And the radius of this, what you can think about is the circumference of this. The circumference of this is kind of like a line, right? The circumference is 2 pi times the radius. So when the circumference expands, it gets larger. It makes the radius expand as well, and we can figure out how much the circumference expands by plugging in alpha, the original circumference, and the final circumference. We can figure that out from the change in temperature. And when we do that, we can find out the new radius, and I found the new radius to be, let me see, 5.6494 centimeters. Okay, and then from that information, I can end up finding the final volume by plugging this new radius back in to find the area, and hence multiply that by the new height to get the new volume, and I got 2,007.97 cubic centimeters. So right around 2,008 cubic centimeters is the new volume of this can. Okay. Now what we can also do is think about what happens to the turpentine. Okay, so of course this can, the circumference gets bigger by linear expansion, the height gets bigger, and so the overall volume that it can hold gets bigger. Well, think about the turpentine. The turpentine is a fluid, and so it undergoes bulk expansion. And remember that the change in volume is equal to the original volume times the bulk expansion coefficient times delta T. And what is the bulk expansion coefficient of turpentine? Well, I looked it up. Different sources differ by a little bit, but it's about 9 times 10 to the minus 4. Probably one of the reasons different sources vary is because the thermal expansion coefficients actually depend a little bit on temperature. So it depends on what temperature range they're doing the measurement in. But about 9 times 10 to the minus 4, and again, that's in inverse degrees Celsius. And so you can look at the original and the final, or the new values of the volume. So the original volume was 2,000 cubic centimeters, right? And the final volume, you can figure out, is 2,108 cubic centimeters, okay? So we can see that the turpentine expands more than the can's volume does. In fact, it expands 100 cubic centimeters more. That means that 100 cubic centimeters, or 100 milliliters, overflows. Okay? So there are 100 cubic centimeters that overflow out of this 100 cc's, overflow when it expands, right? Okay, so that answers the first question. What is the amount of turpentine that overflows? And the second question is then, if it cools back to 20 degrees Celsius, how far below the cylinder's rim is a turpentine surface? Well, that's pretty straightforward to answer, because now when it contracts back to its original size, what's going to happen is the volume is going to go back to 2,000 cubic centimeters, and we will have had 100 cubic centimeters of turpentine overflow, right? So when it contracts back to its original size, there will only be 1,900 cubic centimeters about of fluid left in the can. And so what happens is going to be 100 cubic centimeters that had overflowed, and in so doing, since the cross-sectional area is 100 square centimeters, the new level will be 1 centimeter below the top of the can. How do we know that? Well, because if this area is 100 square centimeters, the volume that overflowed is that right in there. It's 100 square centimeters times 1 centimeter would give you 100 cubic centimeters. So it'll be 1 centimeter below the top of the can. And that is the solution to that problem.